All right, hello again everyone. In this video I'm going to help you to solve problems 691 and 692. Let's start with problem 691. In problem 691 you have to calculate stresses around a wellbore using the Kirsch equations. And for this particular case, as you can see over here, you have what are the values of the total stresses and their direction, and also the value of the pore pressure, and there are two cases for the pressure in the wellbore. So basically, we can interpret this problem as something like this. We're going to make a cross-section of the wellbore. This is a vertical wellbore. It tells us that the minimum principal stress is 4,500 psi and is acting in direction east-west. Let me add a coordinate system over here. North and east. So the minimum principal stress is going to be east-west 4,500 psi, and the maximum principal stress therefore is going to go north-south, always perpendicular because those are principal stresses. And that value is going to be 6,000 psi. Just give me one more sec. I finish with my arrows. This is going to be 6,000 psi. Okay, and we also know that the pore pressure is going to be 3,200. I'm going to add this as a set of arrows in all directions, and this is the pore pressure, 3,200, and you're going to have to calculate stress as a function of the angle theta and the radius for two angles. Okay, so let's see. Let's start with the first case, number 1. Then we have a pressure in the wellbore of the mud of 3,200 psi. So this is going to be the pressure in the wellbore going in all directions. And for the first case is 3,200 psi. Notice that that's equal to the value of the pore pressure. Let me just add the units. Okay. And the problem is asking for what are the stresses, the radial stresses and the hoop stresses for the angle of theta equal to 0 and theta equal to 90. So remember that theta, it is going to be always measured from the direction of the maximum principal stress. In this case, the maximum principal stress is here. This is SH max, and it's going north-south. So the angle theta is going to be measured from the direction north-south. So let me add just an imaginary line over here to help understand what's going on. It's a line which is north-south, and therefore an angle theta equal to 0 will be an angle or a line that will end up along this line. And theta equal to 90 would be will result in a line that would be along this line, where theta, in this case, this is going to be theta equal to 90 degrees. So the problem then asks to solve or to calculate what are going to be sigma theta theta and sigma RR in these two cases. And this is going to start at the wall of the wellbore. This is when R is equal to A, and for a given distance. And I recommend that you do that if the radius of the wellbore, for example, in this case is 8 inches, Well, you should plot these for more or less 5 times that value or 4 times that value. One of the objectives of this problem is to see that those stresses, they get into asymptotic values very quickly. So let me complete this. For example, for theta equal to 90, as in this case, the objective is to calculate what are the hoop stresses and the radial stresses. Notice that the hoop stresses and the radial stresses depend on whether your theta is equal to 90 or if theta, for example, is equal to 0. For theta equal to 0 degrees, now this is the hoop stress and this is the radial stress. And you're going to calculate those two by using the Kirch solution, and here you have the equation. And after you input the values of A and R and the value of theta, let me expand a little bit more. The value of theta, replacing it for 0 or 90, you're going to be able to calculate these two values, sigma RR and sigma theta theta. Remember that here A is the radius of the wellbore, and your R is the distance from the center of the wellbore to the position in which you are. So, for example, your plot should start at R equal to A, at R equal to 4 inches for this particular case, because the diameter is 8. So your plot will start at 4 inches and probably go, let's say, to 40 inches. And what you are going to observe is that the solution should look something like what I'm going to draw here on the right. So let's say, as we were saying before, that PW is 3200 psi, and I want to plot as a function of R starting at 4 inches the value of sigma RR and sigma theta theta. And let's say that also for this plot, I'm going to draw those values for theta equal to 0. Let's start with 0. Okay, for theta equal to 0 degrees, that's going to be this line. And in that line, sigma RR is going to start at a value of PW minus PP, which in this case, PW minus PP is equal to 0. So it's going to be somewhere around there. And it's going to tend, as you go further from the wellbore, it's going to tend to this value, which is the value of SH max. In this case, I'm asking you to plot, remember, effective stresses. So this is going to be 6,000 minus 3,200 psi, which is going to be 2,800 psi. But it's going to be a value higher than 0. So this is going to be something like this. And it's going to tend into the value of SH max. This is going to be for sigma RR. What about sigma theta theta? Well, sigma theta theta at this position, notice that this is the direction of the maximum principal stress. So here I should expect to have something which is a low value, because here is where I would have tensile fractures that either is small or probably it could be negative. And as you go further away along this line, increasing R, at theta always equal to 0, sigma theta theta is going to tend to the far field value, which is this one. It's going to be sigma H mean minus the pore pressure. And in this case, that particular number is going to be 1300 psi. So this is going to look something like this. I'm not plotting the exact answer over here. This is just in a schematic, okay? I'm not going to tell you now the exact answer, but let's imagine that it starts with a negative value. So it goes into a negative value, and as it goes further away from the wellbore, it turns into positive, and it's asymptotic with sigma h mean. This one will be sigma theta theta. And you should repeat this same thing. Let's call it this one A. You can repeat B having the same plot where this is A or 4 inches, this is R, but now you repeat this for theta equal to 90 degrees. And you will see how those values of sigma theta theta and sigma RR, they change. The main goal of this problem is to see how long it takes for these stresses, sigma theta theta and sigma RR, in order to tend to these asymptotic values or far field values. And what you're going to see is that this distance, where there is a relatively high change, is not too long. It's just going to be a few radii of the wellbore, and the objective is to get to know how many. If it's 2 radii, 3 radii, 10 radii, that's what I like that you observe out of this and that you get out of this problem. And then you should repeat the same thing, but now for pore pressure equal to 4,000 psi. All right, so this is problem 691. And for this one, you need to use the full Kirch's equation. Let's continue and talk about problem 692. Problem 692 is a continuation of the problems which are already solved in the notes. You're going to see that you have exactly the same values of stress, the same depth, the same properties of the rock. Something new that you have in this case is that now you're going to have to calculate for the first part of the problem for one, or let me call it A, so it's a little bit less confusing. And you have to calculate what is the pressure in the wellbore for WBO, or breakout angle, equal to 70 degrees. And let me give you a hint, that's going to be less than 10 pounds per gallon, okay? But you will have to calculate that. And I'm going to ask you to repeat this same problem for 3 cases with different values of pore pressure. So there is going to be a solution for hydrostatic condition that we have already worked with, but then I'd like to see another solution for a mild overpressure and another one for a higher overpressure of 0.6. And the objective of this problem is to see how that value of the PWBO is going to change with increasing pressure. As pore pressure increases, you're going to see that your math window is going to get smaller. And these values of PWBO are going to get larger and larger, which means that the lower bound is going to move to the right. And the second part is going to, well, let me finish with the first part. It's not only PWBO what you have to compute, but you're gonna also have to calculate what is the value of PV. So with these two values, and for different values of overpressure, you already have the one for the hydrostatic, you're going to be able uh, to determine the MAD window. And what you are going to see is that if this is your MAD window, and let's say we add an axis here with your overpressure, for an overpressure of 0.44, your MAD window, let me add these two other lines. If this is lambda p, um, for 0.44, probably your MAD window determined by PWBO and by PB might be somewhere over here. And PB. But as overpressure increases and it goes from 0.44 to 0.6, if your calculations are correct, you're going to see that these values are going to start moving PWBO to the right and PB to the left. And this is going to mean that your MAD window is decreasing as the overpressure increases. That's the objective of this problem, to notice that. And the second part of the problem is related to finding what would be the orientation of breakouts and drill-induced tensile fractures for a given state of stress. And in this case, we are taking this wellbore to the Dallas-Fort Worth region. So what you should do is to use the maps of the stress in order to figure out in which direction you have SH max. Here we're dealing with a vertical wellbore, and according to that direction of SH max, you should tell me in which direction you expect to have the breakouts and tensile-induced fractures. Remember that breakouts, well, let's start with tensile-induced fractures. Tensile-induced fractures are going to happen in the general case. Let me do a schematic over here. I'm not doing the solution right now. I'm just drawing the general case. But for a vertical wellbore, if let's say, let me put it at an arbitrary orientation. If this is the maximum principal stress going in this direction, and this one is the minimum, and I have the wellbore, drill-induced tensile fractures are going to align with the direction of the maximum stress. That's where you should expect them to happen, always according to this stress. And breakouts are going to align in a direction perpendicular to the direction of the maximum principal stress. So they are going to show up here. And this is extremely useful because if you know the stresses, as in the case that here I'm proposing, this will be the problem that you know what is the orientation of stress. You could tell what the orientation of these breakouts are and the orientation of the drill-induced tensile fractures, but the opposite is also true. If you drill a wellbore and you run a formation imager through that, you could later, knowing what is the orientation of the breakouts and drill-induced tensile fractures, to tell what is the orientation of your stresses. And remember, that's something that is very important because, for example, for hydraulic fracturing, we want to determine that direction of the minimum principal stress. So if you were to drill a wellbore, a horizontal wellbore, and if we were under normal faulting or strike slip conditions, our fractures would tend to be perpendicular to that minimum principal stress. So we want our wellbore to be in the direction of the minimum principal stress. Okay, so just let me check very quickly if this link is working. And where you should look at in order to check this data. It looks at this. This will take you to the world stress map. And then if you click in this file, it's a little bit heavy, but it's not too large. And after you finish downloading that map, I'm asking you to zoom in into the state of Texas and into specifically a region close to Dallas, and to figure out from that map what is the state of stress and the orientation of stresses in that location. Once you know that, then you're going to be able to tell what the orientation of stresses are and what would be the expected location of breakouts and drill-induced tensile fractures. All right, so you should look somewhere over here near Texas. Probably you need another map in order to figure out exactly where that location is. One more thing about this. Since we have the map over here, I just would like to highlight that many of the orientations plotted in this map are the results of measurements in wellbores. And actually you see over here that one of the methods, or two of the methods used in order to determine orientation of stress, are borehole breakouts and borehole drilling induced fractures, which is what we have just been seeing. All right, that's the end of this video.